Greetings! In today's video, I'm going to show you how to do approximate change questions. To briefly explain approximate change, let's start off with something like this. So let's say we have the y-axis and the x-axis, and let's say we have a curve. So maybe it goes up like this. If we look at a position on this curve, we would give it some coordinates. So maybe I can say that the x coordinate over here is, well, x. And I can say that the y coordinate here is f of x. This is because the equation of the curve itself would be fx equals to something. In such a case, the coordinates of this point would be as follows. Bracket x, comma, f of x. Now let's take a look at another point. Let's say we have a point over here in red that's just a bit to the right of the original point. And let's go ahead and define the distance between these 2 points. So in terms of left or right direction, we'll say that it's a distance p away from the original point. If that were the case, then this point's x coordinate would be x plus p. If that's the x coordinate of this point, its y coordinate would be the function, but instead of taking x as an input, it would take x plus p. So that's f of x plus p. If we were to write out the coordinates of this new point, it would be x plus p, comma, f of x plus p. At this point, since we have 2 points, we can connect them using a straight line. So for example, if I were to draw that straight line, maybe it looks like this, connecting the blue and red points together, that's what it might look like. We can find the gradient of this straight line by using the following formula. The gradient is equal to their y coordinates subtracted together, y2 minus y1, divided by their x coordinates subtracted together, x2 minus x1. Now, something starts to happen when you start moving this red point, the point that's a bit closer to the blue one, and you shift it even closer to the blue point. So for example, if I just get rid of these labels first, so you can move it even closer to the blue point like this, or you can even move it as close as almost on top of that blue point. As that second point in red gets closer and closer to this one here, a truth starts to emerge. Last lesson, we learned that to find the gradient of a curve at any specific point, you just take the equation of the curve, get its derivative, in this case it would be f prime of x, and then you put in the x value of where you want the gradient. So if you're looking for the gradient of the curve at this spot, you put in the x coordinate that's over here. If you wanted the gradient at this spot, you would put in the x coordinate that's over there. And because these 2 points are so close together, when you find the gradient at this specific spot, the original point, the change between those 2 points is so small that the gradient of the curve at that specific point becomes the gradient of the tangent. The tangent line is just a straight line that passes the curve at only one singular point. So not only can we find the gradient of this tangent by looking at the regular gradient formula, we can also obtain it by getting the derivative of the curve and substituting the original x value inside of that to find the gradient of the tangent, which is of course the same straight line. As those 2 points go closer to one another, they practically are on top of each other. So the tangent line is basically the same as the straight line that connects the blue and the red point from just now. So if you can calculate the gradient like this, but you can also do it using the derivative, what we tend to say is that this formula becomes as follows. The dy dx, or the derivative of a curve, is roughly equal. And we say roughly equal because this is an approximation. It's not exactly equal, but it's close enough that we can assume it to be the case. If you were to round it up, it would be fine. The derivative of the curve at any specific point is equal to y2 minus y1 divided by x2 minus x1. So both of these expressions represent the gradient. We're going to simplify this a bit by taking out y2 minus y1 and just representing it like this, delta y. Delta in math means a change, so delta y represents the change in the y coordinate. The x values, as you can see down here, is x2 minus x1. Another way you could express that is delta x, the difference in the x values or the change in the x values. And so for approximate changes, when the change is small enough so that we can assume this to be the case, the derivative of a curve at any specific point is roughly equal to delta y divided by delta x. And that's the formula we're going to use throughout these questions. Let's go ahead and give this first question a try. They say that variables x and y are connected by this equation over here. So this is the equation of the curve that we should be looking at. Find the approximate change in y as x increases from 3 to 3.02. There's a few things that we have to identify first. First of all, this is approximate change. So when the change is small enough, as you can see from 3 to 3.02, it's a pretty small change, then this formula can be used. Not only that, we need to know a few things. First of all, delta y is what we're trying to find, because they say find the approximate change in y. So that's the thing we're looking for. What about delta x? Could we find that? Delta x is the change in x as you go from 3 to 3.02. So the increase from 3 to 3.02 would be 0.02. That's the change in x value. Lastly, the original value of x from the start is 3 because it increases from 3 to this second point. So the initial value of x is 3. We have everything on the right side of the formula, namely delta y and delta x. We just need to find the value of dy dx at this specific point. Let's use the equation to help us out here. So here, y is equal to 3x minus 8 over x squared. You could first rewrite this as 3x minus 8x to the power of negative 2. So if this is underneath a fraction, we can rewrite it as a negative power, x power negative 2. Then let's go ahead and find the dy dx expression. Differentiate y with respect to x. The derivative of x to the power of 1 is just its coefficient, so that's 3. And to differentiate this, we'll bring the power of negative 2 down to multiply. So minus 8 times minus 2 is plus 16. Write back the x, and take the power and subtract 1. Minus 2 minus 1 is minus 3. So that's the expression for the derivative. But remember, we have to find the derivative at a specific point. We're going to use the initial coordinate of x equals to 3 to do that. So we can say at x equals to 3, the dy dx is equal to 3 plus 16 times 3 to the power of negative 3. And you can put this into the calculator, which I'll do in just a second. This gives us 97 over 27. So the gradient of the curve at that specific point is 97 over 27. That's the last tool we need before putting everything into the approximate change formula. Let's go ahead and do that. So dy dx at x equals to 3 would be 97 over 27. And in approximate change, we can assume that that's equal to delta y over delta x. We don't know what delta y is, or the change in y. For delta x, that's 0.02. So to find the approximate change in y, we just rearrange to get this. So this is a divide 0.02. We'll move it to the left-hand side, and that becomes 97 over 27 times 0.02. So putting this on the calculator, we get 97 over 1350. So that's the approximate change in y. As x increases by that tiny amount, y is also going to increase by this tiny amount. Let's take a look at another example, just to get the hang of this. So variables x and y are connected by that equation you see up here. Find, in terms of p, the approximate change in y as x increases from 4 to 4 plus p, where p is small. Let's identify a few things that we'll need first. Do we have delta y? Well, they've asked us to find, in terms of p, the approximate change in y. So that's delta y, and we don't know what that is at the moment. They do say that x increases from 4 to 4 plus p. So the change in x, or delta x, as you go from 4 to 4 plus p, is just p. Remember, it's the gap in between 4 and 4 plus p, not either of those points themselves. So in this case, delta x is p itself. Not only that, the initial value of x that we start with is 4, because it increases from 4. So x is equal to 4. They've also clarified here that p is small, so we can use the approximate change formula. dy dx is approximately equal to delta y divided by delta x. Let's go ahead and find the expression for dy dx. So y is 3x minus 2 cubed. To find dy dx, we'll have to use a chain rule. Let's bring down the power of 3 to multiply. Write back the whole bracket, and then subtract the power by 1. 3 minus 1 is 2. In chain rule, we take our answer and multiply the whole thing by the derivative of whatever is inside this bracket. So the derivative of 3x is 3, and negative 2 doesn't have a derivative. You can then multiply the 3 at the front and the 1 at the back here to give you a 9. So this is the expression for the derivative. We'll go ahead and find its value at this specific point of x equals to 4. So you can say, at x equals to 4, dy dx is equal to 9 times 3 times 4 minus 2, and all of that is squared. So putting that into the calculator, that gives you 900. Just like that. Let's go ahead and use this in the approximate change formula. So if dy dx is equal to delta y over delta x, then that's 900 equals to delta y divided by delta x. Delta x sometimes can be unknown letters. So this is p, which is a small change, as they've told us. So let's go ahead and replace p inside there. P. Then we just solve for y here. So in this case, we move p over to the left-hand side. That will be 900 times p, which is 900p. So at the end, the approximate change in y is 900p, and that's it. Let's go ahead and try this next example here. Sometimes the equations that you will be using will not be explicitly stated. So find the approximate value for the increase in the volume of a sphere when the radius increases from 5 to 5.1 centimeters. Now, when it comes to approximate change, the usual formula that we use is dy dx, or the derivative, is roughly equal to the change in y divided by the change in x. Now, the letters here don't have to be y and x necessarily, because remember, all that this represents is the gradient by using differentiation is the same as the gradient from straight line graphs. For this question, there are two things that we need to declare first. Number one is the volume of a sphere. We can say that volume is equal to the letter v. Other than that, we also have the radius. So we can say that radius is the letter r. So we have v and r. In this case, if we want to find approximate change, it's not going to be dy dx, but rather dv dr. And that's roughly equal to the change in v, which is the change in volume, divided by the change in x becomes the change in radius, or delta r. So this is the formula we're going to use instead. And not only that, we have to also come up with a formula that relates the volume and the radius in the first place, because that's how we'll find dv dr. This is the formula for the volume of a sphere. V is equal to 4 over 3 times pi times r cubed. So we have an equation for V in terms of r. We also have a few important things to note from the question. Delta V is the change in volume. That's what they have asked us to find here when they say find the approximate increase in volume. So we don't know what that is yet. That's what we're trying to find. Delta R is the change in radius. And they tell us that the radius increases, in yellow here, from 5 to 5.1. So that change as you go from 5 to 5.1 centimeters is 0.1. The initial value of r is then 5. So just be very careful there, again, with the change in radius as well as the initial radius itself. You always take the change as you go from one point to the other. And for the initial point, you'll take the starting value. Let's go ahead and find the expression for dv dr. We'll have to differentiate this expression. So we'll say differentiate v with respect to r, which is what dv dr means. In this case, look at the power of r and bring the power of 3 down to multiply. 3 times 4 over 3 is 4. And you also have a pi there, so times by pi. Write back the r and make sure that its power should minus 1. 3 minus 1 is 2. So the derivative is 4 pi r squared. We want to find the gradient, or the value of the derivative, at a specific point. That's when we sub in r equals to 5 into this expression. So you could say here, at r equals to 5, the value for dv dr is 4 pi times 5 squared. 5 squared is 25. 25 times this 4 at the front is 100. So we're looking at 100 pi over here. And that's dv dr. Finally, we can put all of this into the approximate change formula. So dv dr, which is 100 pi, is equal to the change in volume, delta v, over the change in radius, which is 0.1, just like that. You can multiply this 0.1 up to the left-hand side. So 100 pi times 0.1 is equal to delta v. 100 times 0.1 is 10. So 10 pi is equal to delta v. If you want, you can also write this in decimals, but usually you can just leave it in exact form. So I'm just going to write it the other way around here. The approximate change in volume is 10 pi. Keep in mind that the units for volume always have to be in cubed. So if the radius was in centimeters, the volume is going to be in cm cubed. And that is the final answer here. Go ahead and try this question here to see if you can find the approximate change in y as stated over here. Now we're going to find it in terms of p. Feel free to pause the video if you need some extra time. To start, first we have this equation with y and x. So the approximate change formula will look like this. dy dx is equal to delta y divided by delta x. In the question, they want us to find the approximate change in y. So delta y is unknown. Delta x, the change in x, is going to be p, because x increases from 1 to 1 plus p. I'll just highlight this in yellow here. So the change in x is p itself, where p is small. Not only that, the initial value of x, the starting value, is 1, because it increases from 1 to 1 plus p. Now we can go ahead and differentiate the main equation to find dy dx. Here we will have to use product rule. So y is equal to the square root of x times 2 minus 3x cubed. In product rule, go ahead and look for the two things that multiply each other. In this case, it's the square root of x times this whole bracket to the power of 3. We're going to assign some letters to both of these. So I'll say that u is the square root of x. We can also write this as x to the power of 1 over 2. And I'll say that the letter v is equal to 2 minus 3x cubed. First, we will find the derivatives of each of these expressions separately. So the derivative of u, which is u prime, will have us bring this power down. That's 1 over 2 times x. And this power should minus 1. 1 over 2 minus 1 is minus 1 over 2. Then we have v prime. Let's differentiate this using chain rule. So we'll bring the power of 3 down, multiply by the same bracket, and take the power and minus 1. 3 minus 1 is 2. Not only that, for chain rule, we make sure to multiply the answer with whatever is the derivative inside here. So if this is 2 minus 3x, the 2 doesn't have a derivative. The negative 3x has a derivative of negative 3. We can times the 3 and negative 3 together, and that gives us negative 9 out the front. This is what we get. Once you have all of this, go ahead and find dy dx. So dy dx using product rule is u times v prime plus v times u prime. And I'll take this up here, and let me just get a bit of space. So I'll move this over here. In this case, dy dx would be u, which is x power 1 over 2, times by v prime, which is negative 9 times 2 minus 3x squared. Now go ahead and add that with v, which is 2 minus 3x cubed, times u prime, half x power negative 1 over 2. Just like that. Now, you don't need to simplify this expression necessarily. You can do 1 or 2 steps if you want. But what I'm going to do here is just sub in the value of x equals to 1 straight away, because we only need the value of the gradient at x equals to 1. So you can right away, you can just say at x equals to 1, dy dx is equal to, in this case, go ahead and fill in x as 1 in all of these spots that you see in yellow here. So once you do that into your calculator, I'm just going to test it out here. It's 1 power 1 over 2 times negative 9 times 2 minus 3 squared plus with 2 minus 3 cubed times 1 over 2 times 1 power negative half. And that gives me a negative 19 over 2. So once we have that, we can put it into the approximate change formula. Negative 19 over 2 is equal to delta y, which is unknown, divided by delta x, which is p. Once we rearrange for delta y, let's multiply this p over to the left-hand side. So negative 19 over 2 times p is equal to delta y. So the approximate change in the y value is negative 19 over 2p. And that's how we answer this question here. So that's how you use approximate change to find small changes in one variable as another variable increases by a very small amount. If you found this video helpful, please feel free to share it with anyone else who might also need it. And if you're interested in more content like this, go ahead and subscribe to the channel and like this video so that you stay updated on any new uploads. That's all from me for now. Thank you very much for watching, and I'll see you around.